Hi guys, welcome to lesson 7.6, exponential functions. Our objective for today is that I can evaluate and graph exponential functions. In our essential understanding, some functions model an initial amount that is repeatedly multiplied by the same positive number. In the rules for these functions, the independent variable is an exponent. So, we have our key concept here of an exponential function. An exponential function is any function that is in the form y equals a times b to the x power, where a is not equal to 0, b is greater than 0, and b cannot equal 1, and x is a real number. Lots of limiting factors on here. All right, so we've got a couple different graphs of what they look like. We have y equals 2 to the x and y equals negative 2 to the x, and you can see each of these graphs kind of form like half of a U shape. The x-axis is what we call an asymptote, where this line will get infinitely close to it, but it will never touch it. You can never get a function that is an exponential equal to 0. It is not possible. You can get infinitely close to 0, but you will never actually reach 0. So that's a one that has a growth or a positive base, so we're growing. This one is a decay or a reduction, where we are going up, we're multiplying by 1/2 every time, so it's getting infinitely smaller. And if you were to cut a piece of paper in half infinite amount of times, you would eventually start cutting atoms in half. But you would never reach 0 because you always will have some portion of the original that is remaining. All right, so now we're going to identify linear, quadratic, and exponential functions. So we want to look first when we're trying to figure out if something is exponential. If it's data table, we look and see what are our common differences, what's the pattern that we see in the table. So for x, we are adding 1 every single time. We're going from 1 to 2 to 3 to 4, adding 1. Down here on y, what's happening? Well, we're changing our sign, but it looks like we're just adding 2. And we're adding 2, and we're adding 2. So that looks like a common rate of change, 2 over 1, so that is going to be linear. Now, our second example is an equation. Y equals 3 times 6 to the x power. Is it in the form y equals a times b to the x? Yes. Is a not 0? Yes. Is b greater than 0? Yes. And is it not equal to 1? Yes. And x is a real number, so this is exponential. You should be able to spot what a linear equation would look like. Okay? I want you guys to try letters C, D, and write in and then try letter E, because Mr. Boland made a mistake and didn't go through this before he actually recorded it. Okay, so I want you guys to add letter E in there and go through and identify. Actually, no, we should do these because you don't know what you're looking for yet. All right, X, we're adding 1 each time. All right, y values. Are we multiplying by something? Well, this is multiplied by 4, but then this isn't and this isn't, so it's not multiplying by the same thing. Well, let's just look at what we're doing. We're adding 3, then we're adding 5, then we're adding 7, then we're adding 9. Well, that looks like a pattern there. My second difference is plus 2. So, when we find that a first difference, so that first row, the purple row of numbers, if those are all the same, then it's linear, straight line. If our second difference, so we found the difference between our y values, and now we're finding the difference between the differences, if we find that those are constant, which they are, this is quadratic, which is what we're going to get in the next chapter. All right. Letter D, let's take a look at that one. This looks pretty linear. We're adding 4, adding 4, adding 4. plus 1, plus 1, plus 1. So this is linear. Now here's an example of what an exponential data table would look like. First off, you've got your 0 value is 1. That should be a clue that you could potentially be dealing with an exponential, as if one of your y values is going to be a 1, especially if it corresponds with an x value of 0. So that's one of your clues. But the other clue is to look at it and say we're going from 1 to 2, 2 to 4, 4 to 8, 8 to 16. We're multiplying by 2 every single time. Multiply by 2, multiply by 2, multiply by 2, multiply by 2. So if we are multiplying by a common value every single time, it means we're dealing with an exponential. All right. Now, taking a look at problem number 2, evaluating an exponential function. So for these problems, what we're going to do is we are actually going to solve it for a given value. So we're given an equation, and we are going to solve it. So an initial population of 20 rabbits triples every half year. The function f of x is equal to 20 times 3 to the x power, gives the population after x half-year periods. And I want to know, how many rabbits will there be in this population after 3 years? Well, 3 years is going to be 6 half years. Right, because half a year, if we've got 3 full years, 6. So we're going to find f of 6 is equal to 20 times 3 to the 6th power. So when we type in exponentials into our calculator, we do 20 times 3 caret 6. That's all we got to do. Type it in like you've done before. Hit enter, and it's 14,580. Rabbits. Now, if you are in my class, you might need to take that back off of psi mode and put it back into regular mode. Okay. All right. Letter B. Suppose a culture of bacteria doubles every hour. There are initially 2,200 bacteria. The function f of x equals 2,200 times 2x gives the number of bacteria after x hours. How many bacteria will there be after 5 hours? So we want after 5 hours. So f of 5 is equal to 2,200, the amount we start with, times 2 to the 5th, because it doubled every 5 hours. So it doubled, then doubled again, then doubled again, then doubled again, then doubled again. So we're multiplying by 2 5 times. All right, so when you type that in, 2,200 times 2 to the 5th, we get 70,400. So f of 5 is equal to 70,400 bacteria. Okay, so in an exponential relationship, things develop very quickly. Technology operates on an exponential relationship. For a long time, computing speeds doubled every, I believe it was 6 months. All right. Computer mapping software allows you to zoom in on an area to view it in more detail. The function f of x equals 100 times 0.25x models the percent of the original area of the map after zooming in x times. What percent of the original area is shown after zooming in 5 times? And what percent of the original area is shown after zooming out 2 times? Well, that's interesting. That's a little different than we've used before. So we start by saying f of x, actually, sorry, we're going to say f of 5 is going to be equal to 100 times 0.25 to the 5th power. Type that into your calculator, and you get f of 5 is going to be equal to 0.0977%. So less than 1 1/10 of the original map is shown after you've zoomed in 5 times. Now, what about this zooming out 2 times? Well, if zooming in 5 times is a positive 5 exponent, well, then maybe I'm going to be crazy enough to use a negative 2 exponent for my function. So f of negative 2 is equal to 100 times 0.25 to the negative second power. Well, what do we know about negative exponents? We move them to the denominator, so now we're dividing by 0.25, or 1/4 squared. Wow, so we're dividing by a fraction. That's multiplying by its reciprocal. And actually, you're going to find that f of negative 2 is going to be equal to 1,600% of the original area. So more than, 100% of the original area was 100% if we plugged in 0. But if we zoom out twice, we are going to be showing 1,600% of the original area. All right. Letter D, suppose that an investment of $7,500 doubles in value every 12 years. The function f of x is equal to 7,500 times 2 to the x models the growth of the investment, where x is the number of 12-year periods. What is the growth of the investment if it was allowed to continue for 48 years? Well, 48 years is going to be 4 12-year periods. All right, so that's going to be our number for our variable 4. So we have f of 4 is equal to 7,500 times 2 to the 4th power. 7,500 times 2 to the 4th power is 120,000. And we're talking about money. So we do need to make sure we include our units, which are dollars, because we are in the United States. Okay. That would be quite the account to have your money in. All right. Letter A in problem number 3. Problem number 3 is graphing an exponential function. So now we have identified them. We have solved for values with them. Now we're actually going to graph an exponential function. So the first thing we're going to do is I'm going to put an XY table here. All right, and I'm going to plug in just some numbers. Say -2, -1, 0, 1, 2. Okay, and I'll just say 3 for fun. Now, I'm going to put in these numbers. So we've got 0.5 times 3 to the negative second power. Okay. Ooh, I said 3. I did that in scientific notation. I need to do 0.5 times 3 to the negative second power. That's a better number. 0.05 repeating. Okay, and we put the little bar over it. So I've also got 0.5 times 3 to the negative first. Well, that's 0.166 repeating. 0.5 times 3 to the 0, well, anything to the 0 power is 1, so that's just going to be 0.5. 3 to the first power is 3, so 0.5 times 3 is 1.5. 0.5 times 9 is going to be 4.5. And 0.5 times 3 is going to be 13.5. So now I'm going to graph these pieces of data. So the first one is -2 and 0.055. So we're just going to put a point just about at our x-axis on -2. -1, we're slightly bigger. We're up to a whopping 0.166. So we're going to have a point that is basically on our x-axis. At 0, we're up to 0.5, so we're halfway up our grid line. When we get to 1, we're up to 1.5. So you can see already how much this is curved. Now we put in 2, and we're at 4.5, so we're all the way up to there. And then we put in 3, and we're all the way up over here. All right, so when you connect your dot, or when you connect your lines, you should basically start it off as a horizontal line, essentially. But I do not want you crossing over that axis, because it will never cross over. It will always be in the positive y territory if it's positive. It will never, ever, ever, ever cross down below into the negative territory. Okay? All right. So there you go. That's what an exponential looks like. And we have lines on the end because it goes to infinity. All right. So let's take a look at letter B. We've got similar equation. We're just changing the sign from being a positive 0.5 to a negative 0.5. So all of our values are going to remain the same except for their sign. So negative 2 is going to be at 0.055, repeating. Negative 1 is going to be at negative 0.166, repeating. 0 is going to be at negative 0.5. 1 is going to be at negative 1.5. 2 is negative 4.5. And 3 is negative 13.5. So we're going to graph it same way as we did the other one. So again, your point should never, ever, ever, ever cross the x-axis, x-axis, because that is just a mathematical impossibility. Like I said, we call that an asymptote. That is something that you will learn about maybe in geometry, but definitely in algebra too. You're going to deal with this where you're going to calculate asymptotes and do stuff like that. All right. So moving on to letters C and D, I want you guys to try those two problems on your own, and I will go over them for you. So letter C, I create my table of values. I'm going to just start this one at 0, 1, 2, and 3, and maybe I'll go to 4. So 0 has a value of 0.25. Put in 1 for the exponent, it's 0.75. 2 for the exponent is 2.25. 3 for the exponent is 6.75. And 4 for the exponent is 20.25. Again, you can see how quickly things escalate when you start dealing with exponential problems. Okay? That's why anything that is spreading exponentially is something that's worrisome. Right now the flu virus is kind of going exponential. It is, repeating and doubling very, very quickly, and so you can see how entire states could be wiped. Have significant flu outbreaks very quickly. All right, so now we just need to graph these. So I'm going to have a point at 0 and 0.25, so that's pretty low right there. And then I have a point at 1 and 0.75, so it's a little further up. 2 and 2.5, so that's about there. And then we go up to 3 and 6.75, so that'll be about there. And then 4 and 20, that's going to be just like way the heck up here. So far, it was all the way off the screen. It'd be somewhere probably not even there. It's probably even further up than that. But you can see, again, I didn't do any of the negative territory, but you can just kind of infer that it's going to be a line that's going to end up looking pretty much horizontal. Okay. All right, last problem, letter D. We've got y equals negative 0.75 times 2 to the x power. So you're just going to plug some values in for x up there. And I'm going to just plug in some of my own. So I go with 0 and 0.75. Go with 1, which is negative 1.5, negative 0.75. I've got 2, and that's going to be at negative 3. 3 is negative 6. 4 is negative 12. All right, so I can graph that pretty easily. My first point is at 0 and negative 0.75, so right about there. Then we go down to negative 1.5, then down to negative 3, and then negative 6, and then negative 12, which will be right about there. Okay. And we have our exponential function. All right. So what I want you guys to do, make sure you fill out that last page. You may very well be turning that in, so I would be ready and be able to hand that to Mr. Wolf at the door so that you can demonstrate that you actually watched this last night instead of scribbling things down during the announcements, or, I don't know, watching with the sound off for some strange reason. So if you are watching with the sound off, hi, pay attention. All right. Make sure you write down any questions you may have come up with during this lesson and write down a summary of how you identify something as an exponential and how you would go about solving it or graphing that function. Okay, we will see you in class tomorrow for some practice on this, and then the next lesson for the chapter is going to be writing our own exponential growth and decay functions. All right, have a good night.